So now let's look at a situation where we have a non-uniform field. So you can see that I've drawn on this diagram, it's ripped off from the book, I think, drawn in this diagram, and we have basically a point of charge which is creating the electric field. And then I have a point of interest which goes from A and goes around and round and ends up at B. Everything is changing. The distance between the mother charge and the point of interest changes for every point along that line. And the direction between the little bit of direction, my ds, and my little bit of E, that angle is changing for every point. So the whole thing, my electric field strength is changing. Everything's changing. So this is a case where you really need integration. But the basic equation, that delta V equals minus E, integral of E dot ds still holds. And I know, because it's a point charge, that E is equal to KEQ over R squared, where, of course, Q here, let's be careful, Q here is the mother charge, which is that guy there. Remember, for my change in potential, I don't need a charge running on that red line. I just have a point of interest. E dot ds gives me KEQ over R squared, and my ds gives me R dotted with ds. So that's the vectorial bit. So my E is that, my vectorial E is that, and I'm dotting it with ds. Now, here's a little bit that you might not spot, which is to do with this. R dot ds. So the vector R, the unit vector R is there, and I'm going to dot it with that guy there. Well, my unit vector, by definition, has a magnitude of 1, and my ds is a length of ds, and the angle between them is theta. So it's 1 times ds times the cosine of theta. Now, if I look at this little triangle, I'm going to draw the triangle bigger. This is ds, and this is dr, and there's my angle theta. I know that dr over ds is the cosine of theta, so dr equals ds cosine theta. My little bit of change in length, of radial length, is equal to my little bit of change of path length times the cosine of the angle between them. So now I can say, well, my E dot ds is equal to KEQ over R squared, and instead of R dot ds, I can put down ds cosine theta. That comes from there. And then I know that ds cosine theta equals dr, so I come round to here. So I get my E dot ds is equal to KEQ over R squared dr. Okay. So my change in potential is equal to the negative of the integral of E dot ds, which is the negative of the integral of KEQ over R squared dr, which equals minus KEQ minus 1 over R, which gives me delta V is equal to KEQ, that's the mother charge, 1 over RB minus 1 over RA. Now, I'd prefer to use R final minus R initial, just so that there's no mistake about that. They're using B and A, but I prefer to use R final minus R initial. Yes, okay. Yes. Okay. And that's the take home. Okay? So, my change in potential only depends upon the mother charge, because there's no other charge needed. And it depends upon my final distance and my initial distance, but not the direction. Let's think back about our equations. We had that Fe is equal to KEQQ over R squared. And we had that E is equal to KEQ over, big Q over R squared. And then we had our U was equal to KEQ, big Q, little q over R, and our V is equal to KE, big Q over R. There's a pattern we're seeing. And because we're looking at a difference, that 1 over R, if you look, KEQ something over R, because we're looking at a difference, it's 1 over R final minus 1 over R initial. So we kind of could have predicted this just from that pattern that we'd seen before. I'd like you to know that equation. What is the potential difference between a point that is 3 meters to the north of a 2 coulomb positive? So that's 2 coulomb positive. And here's my point, and that's 3 meters to the north of a 2 coulomb positive charge. And the second point that is 6 meters to the south. Oh my word, this is 6 meters to the south. This is P initial, this is P final. So I'm going to say, what is my potential difference? My potential difference is equal to KEQ 1 over R final minus 1 over R initial. I just wanted to make sure that I didn't drop my sign. This has not got a negative sign in front of it. So delta V is equal to KE. My Q is plus 2. 1 over R final is 6. It's not 6 to the south. Who cares that it's to the south? It's 6 minus 1 over 3. Delta V is equal to KE plus 2. 1 minus 6 minus 2 over 6. 1 over 6 minus 2 over 6, which equals KE plus 2 times minus 1 over 6, which equals minus 2 over 6 KE, which equals minus 0.33 KE, and it's going to be in volts. Let's visualize. There's my mountain because it's a positive charge. I'm going from that point there, which is to the north, to that point there, which is the south. I did it I went something like that. However I did it. But notice I've gone down in height. I've gone down in potential. Yep. So you can see I'm using my geometry, my geographical analogy all the time. It really helps me figure out signs and stuff like that. Positive charges are like mountains, negative charges are like holes, and you go from there. And you can visualize it. Cool? So not so bad. You just got to know that equation. Let's say I want to find the electric potential, not the potential difference between 2 points, but the electric potential of a point. So what I say is, I say my change in potential is equal to KEQ V 1 over RB minus 1 over RA. And we say, well, let's compare between a point of interest and infinitely far away. So this is my R final, my R initial And this is my R final. So imagine going from the infinity out to my, I've got to end at my point of interest. So I go from infinity to my point of interest. So then this, is, of course, is R final minus R initial. So then I say, well, it's going to be KEQ 1 over R final minus 1 over R initial, which is KEQ 1 over R final minus 1 over infinity, because that is, my first point is infinitely far away, and 1 over infinity is 0. So I get KEQ over RB, over my R final. And that gives me a positive value for a positive charge. And I guess I said before it was a negative potential. You asked before about, are all potential energies negative? And I said in the Earth they are, yeah. And I guess in this they're not saying that. They're saying you can have a positive potential because I am near a positive charge. So Q is positive. So I am getting a positive potential. Okay. What is the electric potential at a point that's 3 meters to the north of a 2 coulomb positive? So plus 2. Then 3 meters. There's my point. My change in potential equals KEQ 1 over R final minus 1 over R initial. You're joking. Sorry. So that means that my KEQ 1 over 3 minus 1 over infinity, I'm sorry, yeah, V is equal to, because for V I take that point and make it infinite, so that equals KE plus 2, 1, that didn't go well. One over 3, which equals 2 over 3 KE, which equals 0.66 KE volts. Now, I don't particularly remember that V is equal to KEQ over R. I can figure that out from the other one, but you could just remember that, you know. Okay? And if I put a potential, supposing I put a, let's just make this a bit more interesting. Supposing that I put a charge there. So I'll put a minus 2 coulomb charge there. I said, what's the potential? I would go, well, my change, well, I would go my U is equal to Q times V, which equals minus 2 times 0.66 KE, which equals minus 1.32, I think it is, KE joules. So you can always put a charge in, yeah? Electric potential near a group of charges. Yeah. So if I want to find my electric potential, I just take my electric potential from each one of them. So find out the electric potential from that guy there and that guy there, and just add them together. They're scalars. Voltages are scalars. It's joules per coulomb, so it's a scalar. So we just add them up. So we say, consider 2-point charges that are separated by a distance. So what I can do is I can say, well, okay, the potential energy of the pair is equal to the work that must be done to bring the second charge to that location from infinity. So the potential energy Q is Q2 times electric potential. So I work out, I'm trying to work out which, I work out my V at that point, and I multiply it by my electric potential. That's just what I did, basically. So I say U is equal to Q times the potential at that point. Remembering that potential caused by Q1 at Q2 is KEQ1 over that distance. Then I go, well, U is equal to Q2 times V, which equals Q2 times KEQ1 over the separation, which equals KEQ1 Q2 over the separation. If there's a bunch of them, so that's pretty straightforward. We just did what we did. We just did what I suggested. We just put the charge in to the potential and you get it, yeah? You say, what's the potential caused by Q1? It's V. Put charge Q2 there, and that's your potential. That's your potential energy at that point. That's pretty straightforward. But supposing I put a family of charges there, then there's an interaction because of those two, an interaction because of those two, an interaction because of those two. And so what you learn is that the energy associated with all of this, like shoving it all in, is equal to Q1 times Q2 times the separation between them, plus Q1 times Q3 times the separation between them, and Q2 times Q3 times the separation between them, divided by the separation between them. So boom, boom, boom. Just generalizing that expression. Just want to have a quick look. I've got just a couple of minutes, and I'm not going to do all of this, so let's just... Obtaining a value for electric field from electric potential. What we can say is my change in potential is equal to minus the integral of E dot ds, which equals minus E, this is a uniform field, forget that. This is a uniform field, minus E, the integral of ds, which equals minus E times ds. So my little bit of voltage equals my electric field dotted with my little bit of distance. If the electric field has only one component, say in the x-axis, then my electric field dotted with ds equals my electric field in the x direction times dx. My little bit of voltage is equal to minus Ex dx, so Ex, my electric field, equals minus dV by dx, which is volts per meter, and that's where that comes from. My electric field is my slope. If that is my voltage and that is my x, my electric field is like how steep the embankment is. That's kind of where that comes from. This means that components of the electric field in any direction equals the negative of the derivative of the electric potential with respect to the direction. Okay. Why is the negative sign there? Because you're going down the hill. So that's a positive V, but you're going down the hill. So that's why the negative is there. If I want to consider a cloud of charge, I do that same thing, taking a whole bunch of little cubes of it. So I'd say my total potential is equal to Ke times the integral of dq over r. All the little bit of squares, all the little bit of r's. And don't worry about these two. What we find is that, let's take this one. This is the easiest one. We have a ring of charge. It's got a certain radius, and we're a certain distance along the axis that symmetrically goes through the ring. And I want to know the potential there. What's my V here? Can you see how, because of the symmetry, the distance from P to my little piece of charge is always the same? If I'm down here, it's the same. If I'm over here, it's the same. Because I'm going through the middle of the circle. Can you see that? If it was on the plane, it would be the same distance for the radius. I'm above that spots. So it's still the same. It's like a whole bunch of guy wires. They're all the same length. Yeah? So the R's are the same for every little bit. The Q is the total charge. So I said V equals the integral of KE times the integral of, what was it? I've got to go back, I'm sorry. KE integral dq over R. So this is my dq over R. R's constant, so V equals KE over R times the integral of dq. The integral of dq is just big Q, KE over R times big Q. So KE over R times big Q. And R, of course, is just Pythagoras. It's x squared plus a squared. So that looks complicated, but it's not that bad. It's just Pythagoras. So, and this is what you get used to. You get used to looking for, when you get, you know, a squared plus x squared, you know there's some kind of Pythagoras. And even if it's a squared plus x squared to the 3 over 2, you know it's something to do with Pythagoras. So don't let that fake you out. Yeah, last slide. So, electric potential due to a charged conductor. Every point on the surface of a charged conductor has the same electric potential. If not, current would flow. Electric field near a convex points having small radii. The electric field is larger near convex points having a small radii. So points give you large electric fields. The electric field is high near sharp points. That's what that's saying. If I look at my potential, what I see is that inside my potential is constant, and then it falls off as an inverse relationship. And for my electric field, said before, the electric field is 0, and it falls off on the outside as an inverse square. KEQ over R. Yep, okay. That's it. So, I've still got some work to do to make it kind of like smoother, but what do I need you to know? I think that's a really valuable page, because it's saying, hey, you know, it's just a uniform field. It's delta V equals minus ED, or delta U equals minus Q delta V. It's Q delta V, which is minus Q ED. And doing the IJK is always nice. So that's a good skill set to have. And then for that, it's just knowing that equation and knowing how to use it. And then there's knowing that equation and knowing how to use it. And then I suppose there's knowing that equation and knowing how to use it. I'm not so interested in that. This is more background. And that didn't take us anywhere of interest, I don't think. I could give this question. I suppose I could give this question because it looks hard. It's a bit of a gift. It looks like a bear. And yet you're just going, oh yeah, it's just like KEQ over R, but R is Pythagoras. So it looks horrible. And when as teachers, when you show each other's exams, people go, oh, look at that. That's an intuitive. Look at that. And you go, well, think about it. It's not bad. But these other two are completely out of whack. I wouldn't ask you these two. We just go too fast for that. That's one of those examples where when I was in college, we had time to look at that because we'd already done all the other stuff. And for you guys, although it's still in the book, I don't think we have time to do that. Okay, cool. So, Monday. So, first 4 sections. It's all on oscillations and waves and sound. Look at the old tests. I look at the old tests. I go, I don't want to blindside you with, I always like to have a new question somewhere, if I have time. But I don't want to blindside you with like 16 new questions that you've never seen before. I want to reward people who've sweated the detail and done the homework and done the old test. That's no guarantee, but that's my intent. And so I look at the old test and I kind of go, let's finagle this a bit, let's change that, let's change that. Oh, let's go to this other test and pull the question in. So I try to be reasonably conscientious about making it so that it's not, you can't just dial it in. But I don't like that, my daughter's going through it, that shock and horror you get when the teacher completely misunderstands where the class is. My daughter just had it. And nobody could do the test. And it's like, that's not her. She came home and she was like, everybody was crying. Nobody could do that science test. And I said, well, that's okay, because nobody could do it. It means that there's a problem. The teacher was expecting, they weren't thinking it through. They'll learn, And as a teacher, I try to avoid that. I try to make it so that, if you work harder, it's more accessible, without making it so that you can just do it just because you've seen it so many times and you don't really know what's going on. See what teaching's a very interesting career. You should think about it. It's a good career. Oh, that was all on the recording. That should be there.